Do you click too many photos? Or extensively use a mobile phone for shopping online in lockdown? Maybe you love ordering food online. But what do you do when all of these devices which you use get discharged? Charge them right, using batteries. Well, actually there's more to it. So let's find out. These batteries are actually called lithium ion batteries, which are incredibly popular these days, and you can obviously see why. You can find them on smartphones, cameras, laptops, etc. But there are certain downsides to it too. Their efficiency becomes limited by ionic transport, which is especially detrimental in the transport within the liquid electrolyte. Measurement of practical lithium diffusivity within the complex has been a challenge. Therefore, we will be presenting about the effective mass transport properties in lithium ion electrodes. Hello, my name is Sajal and I'll be your companion from here on. So let's get started. Here we have a toy diagram of a battery which can be largely broken down into a collector part, electrode part and electrolyte part. Charge is transported across the entire battery, governed by various constituent relations for the transport through each part and at the interface between parts. There is a net potential gradient developed across the electrodes which facilitates unidirectional flow. Here we can see graphite and metal oxide electrodes, which is only for illustrative purposes.
Hello all, this is Parth Kanani. I am going to present a macroscopic charge transport model for ions in battery. Let's review with some basics. Here we have written electric field E as the negative of a potential gradient, and we have the divergence of the electric field as the charge density as expressed by the Gauss law. Charge density is written as F Faraday constant times the difference in the concentration of negative and positive species. We go over some conservation laws. The rate of change of concentration for each negative and positive species added with their respective divergences of molar fluxes can be written as 0. This is the basic conservation law for charged species. Now the molar fluxes can be written as the concentration times the drift velocity of the given species, which is contributed to by two terms, the diffusion term and the migratory term. The migratory term is due to the presence of electric field and the diffusion term is due to the presence of concentration gradients. The diffusion term is written by Fick's law, where dP is the fixed diffusivity, and then we impose charge neutrality constraints and we write Cn equal to Cp equal to C. Now the conservation laws can be rewritten as follows, where I can be anything P and N. Now if we add these equations with P and N, we get an equation as such, which has direct analogies with Fick's second law of diffusion. The D effective can be written as dN dP upon dN plus dP into 2. If we subtract those equations and define J, charge current density, as F times Cp minus Cn, we get the divergence of J equal to 0, which means that the current density is conserved within the band. We can also derive Ohm's law from this interestingly. It is easy to see that the Ohm's law can be easily written as kappa, the electrolyte conductivity, times the electric field, and this extra term is due to the presence of concentration gradients within the electrolyte. It can be easily seen that the electrolyte conductivity as a function of concentration can be written as such, and the transference number is a constant written as the ratio of diffusivity. Now we write a new set of equations in which we relax certain modeling assumptions. Notice that in here we assume that D effective is constant and independent of concentration, K varies linearly with C, and the transference number T plus is also a constant. We also assume dilute electrolyte and stationarity conditions, all of which are not compatible with experimental data. So we relax certain assumptions and we let D effective vary with C, incorporating non-stationarity. Notice how this second derivative is still expressed as the divergence of a scalar times a gradient. This is a varied form of Fick's law. We still have the current density conservation, and the Ohm's law is tweaked a bit, where instead of the previous we have a factor of 2 right here. The new effective diffusivity, conductivity and transference number can be written as such, and instead of the concentration gradient we have the gradient of a quantity mu e of C by RT, which has the same dimensions as concentration upon concentration gradient. Now the microscopic model for interface transport will be explained by Siddhant.
We shall also use the Butler-Volmer relay for electrochemical kinetics, which gives us the transfer current density JTI. This equation accounts explicitly for the non-steady nature of the transport process. It is important because this is the only relation in which the characteristic time scales of the process are embedded. We can see it as a function of potentials and concentrations of both solid and the solvent phase. We will skip the expression and its derivation, which all the simple does not come out from mass transfer principles. We shall assume that the electrode can be subdivided into an array of cells over which the electrode structure is locally periodic. That is, the structure inside neighboring cells is virtually identical but may differ significantly between cells separated on the macroscopic length. An example of cell microstructure around an array of ellipsoidal electrode particles is illustrated in figure 4. Let's average the problem using homogenization. These consist of macroscopic equations for the lithium ion concentration C and the electrolyte potential phi, which is measured with respect to a lithium electrode. These are formulated in terms of the microscopically volume average lithium ion flux QP, the microscopically volume average current density J, and the microscopically surface average transfer current density JTR. These average quantities are formally defined in terms of integrals over the microscopic cells as follows. The macroscopic equations homogenized now look like as follows.